Welcome back, mathematicians. Um, this lesson is going to be on graphing direct proportions. And again, it's going to be on my iPad, so this digital version should look like your paper version. Um, so if you want to pause it and you can write down this table, I thought we'd do some kind of applications to what's going on uh, in the real world right now, which is the coronavirus that's spreading. And what's interesting about that is there's a value called R naught, um, and that value is a proportion. And mathematicians, statisticians, what they do is they use this the formula to come up with a proportion of how likely that person that is infected with a virus will spread that disease to a certain amount of people. So right now, they're saying that that value is 2.2. So if we were to write a direct proportion equation for the coronavirus, we would say that it's y equals 2.2x, because for every one person that's infected, we can expect there to spread to 2.2 other people. So obviously you can't have a 0.2 of a person, but when you use statistics, we often use decimals because as we start to get our range bigger, right, that 0.2 of a person starts to become a whole, and we don't want to lose that amount. So oftentimes, uh, even though it doesn't make sense to have 2.2 people, um, we will still use that number. So when we extrapolate and expand the data, we don't lose anything. Um, but let's talk about some key aspects about graphing direct proportions. Um, what we want to show on a graph is exactly what's on the table of information. Okay. In order for something to be a direct proportion, it has to start at the point 0, 0. So I know you know how to plot points. Okay. So in order for this to be a direct proportion, and our data says that it is, the first value is going to be 0, 0. And that makes sense in this context because if you have 0 people that are infected, you would expect there to be 0 people that will then get the infection, right? That would be the expected outcome. Um, and then we can keep going. So let's try 1. We would say that it's about 2.2. Okay, and I'm just getting this information because 2.2 times 1 is 2.2. So I'm kind of filling in the table, and then I'm going to fill in the graph. So 0, 1, do 2, and then let's do 4. Okay, so to fill in for 2, we would do 2.2 times 2, and 2.2 times 2 is 4.4. And then to do 4, we do 2.2 times 4, and that would be 8.8. So that would be kind of the expected outcome. If you have 4 people that are infected, you would expect that to spread to 8.8 people. Now, in the real world context, this value doesn't mean that the people that um, have that specific virus are going to show symptoms. It doesn't mean that you know they're going to die from that virus. All it means is that they might have it, because you can have this coronavirus, but it doesn't mean that you're going to show symptoms. It's kind of like the flu. You can have very mild symptoms of the flu, or you can have like the full-on flu, which is really bad. Okay, so I just thought I'd bring this into kind of like a bit more relevance of what we're talking about today in the news. Um, so let's graph this then. Okay, so we're going to start at 0, 0, and that's really important. If it doesn't start at 0, 0, it's not a direct proportion. So we can actually put that down right here. In order for it to be a direct proportion, it has to start at 0, 0. So that means if you have 0 of nothing, you have 0 of the other thing, which makes sense in this context, and it'll make sense in other word problems as well, right? If you have 0 gallons of water, you can't have any fish, right? That would be a reference to our last lesson. Okay, so it's to start at 0, 0. So that's 0 on my x-axis here, which would stand for the number of people that are infected. Okay, and that's 0 on my y-axis, which stands for people that get the virus, or people that it spreads to. Right. The other important thing is, as we start to plot these points, right, our next step is going to be to plot the points. We have 1, 2.2, so I skipped a line, then went to 1, skipped a line, then went to 2, skipped a line, then went to 3. You have to be consistent when you do this. So if you leave 2 blocks before 1, you have to leave 2 blocks before 2, 2 blocks before 3. Okay, so you can't make a mistake or your whole graph's going to be messed up. So we definitely don't want that to happen. Let's zoom in a little bit on here. If one person is infected, we can expect 2.2 people to get it, and we'll say that's about here. If 2 people are infected, we can expect 4.4. So it's pretty close to 4.5. We'll put that there. Right. I actually skipped 3, and I went right to 4. If 4.4, if 4 people are infected, I can expect 8.8 to get it. Okay, so as you can see, that actually goes off my graph, which is okay. Your table can go off your graph, but we have enough points here where we can actually make a line. So that's what we want to do next. We're going to make a line through the points. So draw a line through the points. Kind of like connecting the dots. Remember, it's going to start at 0, 0. So now we're going to have a line that starts at 0 and goes through those points. Okay, and technically, that line's not going to stop. So we want to put a little arrow there. We're not going to put an arrow here. It actually wouldn't go down to the negatives because you're not going to have negative proportions in this instance. Okay. And now one other key aspect is we talked about the constant of proportionality, or that value k. Okay. You can tell where that is on a graph by looking at 1. This value here is the value for k, right? Which is your constant of proportionality. Okay, so when x is 1, okay, y is the constant of proportionality. Right, which is also the variable k, because y equals kx. So whenever you're asked to give an equation based on a graph, all you have to do is look at where 1 is and what the y value is, and that'll tell you what the value for k is. Okay, and then there's another key point in graphing direct proportions. If you remember before in the last lesson, when we looked at all of these ratios, they never changed, right? 2.2 divided by 1 is 2.2. 4.4 divided by 2 is 2.2. 8.8 divided by 4 is 2.2. Right? All those ratios are the same. That's why this makes a straight line, because that ratio doesn't go up or down. It doesn't make this line bend. Okay, so in order for a graph to be a direct proportion graph, it's also going to be a straight line. And from that, we can move on to example 6, which is the first example in this lesson. And we're just given A, B, and C, and we're asked, does each of these graphs represent a direct proportion? And if it does, find the constant of proportionality. Okay, so the two things you have to ask yourself, right, is does it start at 0, 0? So let's look at A. A starts at 0, 0. So we can say that's good. This does not start at 0, 0. All right, this one starts at 0, 10. Don't want that. And this last one does start at 0, 0. Okay, so now we have two possibilities, right? We already know it's not going to be this one because it doesn't start at 0, 0. It starts at 0, 10. Now let's look. Does it make a straight line? So this is a straight line. Right, so I can put another check mark. This is a straight line. So I could put a check mark, even though it's still not going to meet the criteria for a direct proportion. And this one is a curve. Okay, that means that in the table for this one, those ratios are not going to be proportional. They're not going to be equal to each other. Okay, so that would not qualify then. Okay, so the answer is going to be yes for this one. And then the constant of proportionality, the COP, is going to be right where 1 is. So the constant of proportionality is 10. So it's really easy to see from a graph. You just look at where 1 is. That's my value right there. Okay, this one is not a direct proportion, and this one is not a direct proportion. And lastly, it says write a direct proportion equation if it is. And since I know that my constant of proportionality is 10, and my direct proportion equation is just that generic y equals kx, where you fill in a number for k, my equation for this one is going to be y equals 10x. And then we're not given a word problem, so we don't have to say what the proportionality represents. If we were given a word problem, like we were given this graph up here, we would want to say, well, it represents that when one person is infected, then you can expect 2.2 other people to get it. But we're not given any type of situation for this example, so you don't have to worry about that. Our final example is about Jonathan, who works at a bookstore. The amount of money he earns is directly proportional to the number of hours he works. The graph shows the amount of money, W dollars, he works in T hours. So we're given the variables W and T. Your graph is blank, but they actually give you this graph, so I've written it down here if you want to copy it down. You can also see it more clearly if you look at the textbook. Okay, the textbook has the graph. But what we're going to do is we're going to decipher this graph and answer these questions A through F. So let's take a look. Find the constant of proportionality. How much does Jonathan earn per hour? Well, if you remember from the first example, all we have to do to find the constant of proportionality is we look at where 1 is. And 1 on the graph is at 15, right? So 1 hour is $15. Okay, so how much does Jonathan earn per hour? Well, he earns $15 per hour. Write a direct proportion equation. So we have our constant of proportionality, right? Which is 15. So when we're asked to write a direct proportion equation of y equals kx, that means our equation is going to be y equals 15x. Now it says explain what the point 230 represents in this situation. So if you go back to that blanket statement from the last lesson where you had to explain the meaning of the numbers, we're going to go back to that and we're going to use that with these numbers. So if 2 represents the number of hours, and we can zoom in on this graph a little bit, 2 represents the number of hours, 30, right, is this point here. So to explain what that point represents is that if Jonathan works for 2 hours, he earns $30. So Jonathan earns $30 for working 2 hours. Which is if Jonathan works 4 hours, how much will he earn? Well, let's take a look. So we've got 4 here. If we go up to 4, that point is at 60. So he'll earn $60. If Jonathan wants to earn $45, how much should he work? So in this case, we're going backwards, okay? So we're working backwards. And we're going to say, okay, so $45 is here. And where would that be? That would be at exactly 3 hours. So that's fortunate, right? Because it was exactly on 3. So we can put 3 hours. That's not always going to be the case. It could be like 2.5. You have to kind of estimate a little bit. In this case, it was nice though. Okay. How can you use the graph to find the number of hours Jonathan should work if he wants to earn $65? So it's kind of like explaining what we would do for E. When we go to the graph and we look backwards, all you would have to do is put your point at 65 right? Then go over and you'd want to extend the line. Okay, so if we extend this line and we zoom in, okay, at 5, if he's earning 15, we would expect that to be about $75. So what we would do is we'd work backwards and we'd put a line at $65 for the wages earned and figure out where that falls on the line. And that's how we want to answer it. So work backwards, like part E, but extend the line. So you know where the point is at. And now you should have enough information to move on to the textbook problems. There's no practice problems for your notebook to have your teacher check, so you can move right on to the textbook practice.